Hi everyone. Today we're going to be looking at section 9.2 from our textbook, which is titled Logarithmic Functions. This is a topic that you likely have not seen much before. Logarithms and logarithmic equations, functions. So we're going to dive in and get all the basics of logarithmic functions. In the next section 9.3, we'll see some properties, how we can use them to solve various types of logarithmic equations. But today we're getting the general idea. So let's start taking a look. So logarithmic functions, first thing you need to know. In 9.1, we talked a lot about exponential functions. Logarithmics and exponentials are somewhat inverses of each other. If you look at this graph down here on the screen, you can see that just like we talked about inverses back in chapter 7, their graphs are reflected over that identity function, over that y equals x function. Now, here's what I really want you to focus in on right now for what's on the screen. What I just highlighted in yellow. So that right there in math terms in English is pronounced log base 4 of 64. So a couple things to note. The little number down here is what is known as our base. And you might remember that word from 9.1. The base is what is being raised to an exponent. So what is log base 4 of 64? Well, I'm here to tell you that it's actually 3. And why is that? I'm going to give you the snapshot, just a quick glimpse right now, and then we're going to see the process and some examples with this. Log base 4 of 64 is another way of saying 4 to the what equals 64. These two statements are exactly the same. They're just written differently. 4 to the what equals 64. And if you think 4 times 4 is 16, times 4 is 64. So 4 to the what equals, this is 4 cubed. So it must be 3. And that's how I knew the answer was here. Logs and exponentials, I should say, can be written as each other and translated. And that's the first thing we're going to be looking at, is translating between logarithmic and exponential forms, writing the same thing a different way from what it currently is. Now, a little later on in this video, I'm going to show you the math behind this trick, but right now I'm just going to tell you what the loop refers to. This is how I always think of it in my head when I'm translating. So first one right here. Log base 3 of 27 equals x. If I were asked to write that in exponential form, we know what exponential form looks like. It's something to the somethingth power equals something else. There are 3 things we need. So here's what we're going to do. Start at the bottom, the base, draw a loop around the equal sign, and come back. That gives us the order that we want to write these numbers in our exponential form. 3 to the xth power equals 27. Now, let me back up and kind of repeat that, say that again. If we're just trying to translate into exponential form, which is boxed there, all I'm going to do, I'm going to start at the base, draw a loop around the equal sign, and then write those values, the 3, the x, and the 27, in the order I encounter them. 3 to the xth power equals 27. Because we know that's what exponential form should look like, something to an exponent. Let's try another one. Log base 2 of x equals 10. Start at the base, loop around the equal sign. This translated would be 2 to the 10th power equals x. Another way of writing the exact same thing, it just looks a little bit different. All right, so take just a few seconds and try this one. Log base x of 16 equals 2. How would we rewrite that? Give it a shot. I'll wait 5 seconds. All right, start at that base and then write those values the order that we encounter them. X to the second power equals 16. So this is what I mean when I say the loop. The loop, as I mentioned before, later on we're going to see the math behind it, why it works, what is actually happening. But it's a really handy way of just translating from logarithmic form into exponential form. Start at the base, loop around the equals, and come back. Now, what if we wanted to go the other way? If you look at those equations on the right, they are already in exponential form. Something to the something equals something else. So here, I'm starting in exponential form. If I want to go to logarithmic form, kind of similar. I know that logarithmic form is log base something of something equals something. I still need 3 values to plug in. So here's how the loop works if we start in exponential form. Still start with your base, that's what's being raised to an exponent, and loop around to the exponent. Log base, what's the first thing I encountered? Log base 5 of 100 equals x. This is the exact same statement, just written in logarithmic form. And you can check it. If you're familiar with the other loop, you can say, okay, well, start at the base, loop around, that would give me 5 to the x equals 100. And that's exactly what I started with. So you can always kind of check your answer if you know one of these loops. Let's try another one. 21 to the second power equals x. Start at the base, loop around. So log, I know I'm trying to get into logarithmic form, so I need to know what that looks like. Log base 21 is the first number. Then we get to the x, so log base 21 of x equals whatever the exponent is. One more for you to try on your own to put it in logarithmic form. Give it a shot. And I'll just wait a few seconds. Start at the base, log base x of 512 equals 9. And it's now translated into logarithmic form. So a couple statements about what we just did, what's on the screen right now. We have not really solved anything yet. We have, though, taken something written in logarithmic form and turned it into exponential form. That's on the left in red. We have taken something in exponential form and turned it into logarithmic form. That's on the right. At various times in these problems, it may be more convenient and more helpful to have it in either exponential form or logarithmic form. So this is an important skill. You're going to have some practice problems on this, just going back and forth to make sure that you have the ability to translate it into whatever form is most convenient for you. So that's the loop. And so now let's use the loop a little bit when we're evaluating logarithmic expressions. You're on the street and someone walks up to you and says, hey, what is log base 2 of 64? And you need to know, what is the answer to this problem? What does this mean, really? So here's the technique that I recommend I would show you. We're trying to figure out what log base 2 of 64 is. I'm just going to name it something. I'm going to say, okay, that whatever that is, it equals x. So when I get x by itself, I'll know that I found what I was looking for, because I'm naming whatever this value is, log base 2 of 64, I'm naming it x, and then I can write an equation and try to get x by itself. So I'm hoping by adding that variable there, you see what we're going to do. We're going to say, okay, well, let's loop it. We're a little bit more familiar with exponential form. So I'm going to loop it, start at the base and loop around and say, okay, so 2 to the xth power equals 64. 2 to the xth power equals 64. And so in the next section, again, we're gonna learn some different techniques to approach this problem. But right now, all we have is 2 to the what equals 64? Well, what is 64? If you pull out your calculator, you might say, I think 64 is a power of 2. 2 to the 4th? No, 2 to the 5th? close. 2 to the 6th, it looks like it should be. So 64 is 2 to the 6th power. So we can say, well, 2 to the x equals 2 to the 6th. And then if you remember from 9.1, the 2's are the same, the bases are the same, so the exponents must be the same. X equals 6. So what did we do? Log base 2 of 64. We gave log base 2 of 64 a variable. We said it would equal x, and whenever we get x alone, we know we've solved our problem. We've used the loop to write it in exponential form, 2 to the x equals 64. We made sure that, we knew what 64 was. We used our calculator, 2 to the 6th power. So if 2 to the x equals 2 to the 6th, x must equal 6. Let's do another one. Log base 9 of 243. And just like before, I'm going to give it a name. I'm going to call it x. And when I've solved for x, I'll know I'm done. So let's loop it. 9 to the xth power equals 243. And I'm not really that familiar with 243. So I might say, okay, 9 squared, maybe? Now that's 81. 9 cubed. And that's 729, which is too big. So it doesn't look like we can rewrite 243 as 9 raised to an easy exponent. So what do we do? If you remember, we saw this in 9.1. We say, well, can I write it as 3 to the something? Because I can write 9 as 3 squared. I could say, okay, so this is 3 squared to the xth power without changing anything mathematically. 3 to the 3rd is 27. 3 to the 4th is 81. 3 to the 5th is, there it is. 3 to the 5th is 243. So I'm just going to call this side then 3 to the 5th. Just like in 9.1, exponent rules. 3 to the 2x power equals 3 to the 5th. Now that the bases are the same, 3 and 3, we're comparing apples to apples. So we can just say 2x equals 5. Divide by 2 on both sides. X equals 5 halves. So 9 to the x equals 243. We got that from the loop. We had to use that trick from 9.1 of getting them in the same base. In this case, we had to rewrite both sides of the equation so that it was 3 to the somethingth power. And then once we got the bases the same, we just had to solve the exponents. So I want you to try this one. Log base 2 of 1/32 starts you off by saying equals x. And I will challenge you to loop it, write it in exponential form, and try to figure out 1/32 is 2 to the what? 2 to the what power? If you're kind of stuck, confused, think about your negative exponents. I'm going to pause the video and work it out on my screen. I'm going to ask you to do the same. Pause it, try it, and then hit play, and we'll see if our work matches. All right, I've got my work on the screen. Log base 2 of 1/32 equals x. So 2 to the x equals 1/32. And I gave the hint before I paused my video of negative exponents. I kind of showed it here. I said, okay, well, 32 is 2 to the 5th power. So 2 to the x equals 1/2 to the 5th. And if you remember your negative exponent rules, that's the same as 2 to the negative 5th. So in this problem, x equals -5. All right, one more of these types of problems right here. It's a little bit different. It has an x in it already. And so when we're naming this, log base 4 of 16 to the xth power, can't use x. X already means something in this problem. I'll just call it y. I'll take that next letter in the alphabet. So this one's a little bit different because here, when we loop it, we see 4 to the yth power equals 16 to the xth power. Now, what are we trying to solve for in this problem? We're trying to get y by itself, because as soon as we get y by itself, we know we've solved it because we decided that the original problem statement that we were being asked is equal to y. So we just got to get y by itself here. So rewriting the sides so that the bases match, I see 4 to the y power equals 4 squared to the x, because 4 squared is 16. 4 to the y power equals 4 to the 2x. Bases are the same. We can just set the exponents equal to each other and we get y equals 2x. Now this might not seem satisfying because you say, well, but what is that number? What is that value? Because we had an x in our problem statement, 4 to the something equals 16 to the x, we won't get just a numerical result. This is saying whatever x is, y is 2 times that value. Because we don't currently know what x is, but as soon as someone tells us, y will be twice that value. So I wanted to show you one like that because occasionally you do see those problems where instead of like these 3 red ones where x equaled 6 and 5 halves and -5, we get an expression for our answer for the problem statement. All right, so just some practice evaluating those logarithmic expressions. Now, here's where some of that fun begins a little bit, where we get back into the theory of logs and exponents and why does the loop work? What is actually happening? I'm going to show you that right now. Logs and exponents at the beginning of this video, we said were inverses. So logs and exponents undo each other. They counteract. It's kind of like addition, subtraction, or multiplication, division, logs and exponents. So here's what is actually happening with the loop. I'm going to zoom in on this first problem. And we see that log base 5 of 125 equals x. Now, with the loop, we would just do this and we would say, okay, so 5 to the x power equals 125. And that works, and that's nice. But what is actually happening? What we are doing mathematically is we are raising 5 to the left-hand side equals 5 to the right-hand side. This is something we can do. We're doing the same thing to both sides of the equal sign, so we're keeping this equation. 5 to the left equals 5 to the right. Now, why did I choose 5 specifically? Because that was my base. And 5 to the log base 5 counteracts. They counteract each other. They cancel each other out. We get 125 equals 5 to the x power, which if you'll notice is exactly what we got with the loop, right? 5 to the x equals 125. So this is mathematically what's going on. And this is how a lot of times I am going to demonstrate 5 to the left equals 5 to the right, or whatever that base is. Because especially when we get to inequalities at the end of this lesson, it's good to show your work and represent it that way and not with the loop to make sure our inequality sign stays going the same way. Let me really quickly, though, finish this. So 125, I happen to know that one. That's 5 cubed equals 5 to the x power. So 3 equals x. So that's what's actually happening with the loop, is we are getting rid of the log by going whatever the base is. In this case, it was 5. 5 to the left equals 5 to the right. And when you do 5 to the log base 5, they're gone. Okay. What would we do on this one? Similar. Log base 2 of x equals 8. So I'm going to raise both sides into the exponent. 2 to the log base 2 of x. Again, I chose 2 as my base because that way the 2 log base 2 cancel. 2 to the left equals 2 to the right. X equals 2 to the 8th power. And fortunately, I have my calculator. 2 to the 8th is 256. X equals 256. Pretty quick problems when you understand some of these fundamental concepts. What about this one? Try this one. Try showing your work without the loop. Try showing it with raising the left and the right into the exponent. So pause the video, try it yourself. I'm going to work it out on camera for the video just so you have it. So once you've got it, unpause and see if your work matches mine. I'm going to say 9 to the log base 9 of x equals 9 to the 3 halves. 9 to the log base 9 cancel. X equals 9 to the 3 halves. 9, not divided, 9 to the 3 halves equals 27. X equals 27. So yes, the loop is quick and convenient, but this is what's going on underneath the hood. And this is something you should know, especially when we get to inequalities. So a couple other scenarios, extraneous solutions, we've heard that term before throughout this course. There are some solutions that will seem to work. You do everything right, and then when you get to the end, you plug it back in, it actually doesn't work. And so here's what that looks like. Log base 14 of m squared minus 30 equals log base 14 of m. Well, to get rid of that log base 14, because I just have log base 14 on the left equals log base 14 on the right, I'm going to raise both of them into the exponent. 14 to the log base 14 of m squared minus 30 equals 14 to the right-hand side. 14 to the log base 14 cancels out on both sides. M squared minus 30 equals m. And we've spent a ton of time this year talking about how do we solve quadratics. I'm going to factor. I'm going to move that m over. M squared minus m minus 30 equals 0. I know m and m. I know my signs are different. Multiply to be negative 30, add to be negative 1. I'm thinking minus 6 plus 5. So m equals negative 5 or positive 6. Negative 5 or positive 6. Okay. So from factoring, that seems to work. However, I'm going to introduce right now a really important concept and the main cause of extraneous solutions. Now, on my calculator on the screen, I don't have a log base 14 button. All I have is a log button. And so I'm going to ask you right now to take my word for this, that these logs work kind of the same way in this regard. Log of 5, according to my calculator, is that ugly decimal. Log of 8 is that decimal right there. But what is log of negative 5? It gets an error. It's a non-real answer. So here's the concept I'm putting forth and using the calculator to demonstrate. Whatever is inside the log function, whatever we're taking the log of, has to be greater than or equal to 0. And you just saw a demo on the calculator. When I tried to do log of negative 5, I got an error. Log of negative 1, I will get an error. What about log of 6? That was my other answer. Oh, that one works. Okay. So as you're going through, whenever you get an answer when you're solving these logarithmic equations, you want to stop and plug it back in and say, does it work? So if I plug in negative 5, log base 14 of negative 5 squared minus 30, does it equal log base 14 of negative 5? And immediately on that right-hand side, I say, wait, log of a negative, that cannot work. But what about if I plug the 6 in? Log base 14 of 6 squared minus 30. So that would just be log base 14 of 6, because 36 minus 30 equals log base 14 of 6. Everything is positive. They equal the same thing. M equals 6. So make sure, if I get rid of that, make sure that when you get a solution, you plug it back in, and we're never taking the log of a negative number. You'll notice up here, everything we did was positive, log of a positive number. So make sure that you're always plugging in to check for those extraneous solutions and making sure you're only taking the log of a positive number or 0. What do you think? Can you do log of 0? Nope, you can't. And I'm not going to explain that because we'll cover it in a future section. Sorry, I had to think ahead just a second there. But always has to be that positive number. Okay, so last 2 problems. And the good news is pretty much everything on here you've seen either in this video with logs or in other parts of the course and other sections. Inequalities work largely the same way. But we have to keep in mind the domain. So we find the domain, we solve the inequality, we graph it on a number line and test, and then we write our final solution. So just 2 problems to look at with this. First one, log base 4 of x is greater than 3. Let's do step 1. Step 1, the domain. Well, I know that I can only have positive numbers inside there, right? Positive numbers inside that log, I should be more specific. So whatever is inside the log, x needs to be greater than or equal to 0. Okay, and I shouldn't have said greater than or equal, sorry. Greater than 0, because we just saw that 0 doesn't work with a log. So x needs to be greater than 0. That's my domain, that's step 1. Step 2, let's solve this inequality. I'm gonna say 4 to the log base 4 of x is greater than 4 to the third. So 4 to the left equals 4 to the right. That means x is greater than 4 to the third power. And if you don't remember from earlier in this video, 4 to the third power is indeed 64. X needs to be greater than 64. So domain, I'll just put a blue star by it so we know that's my blue work. Solving, that was my red work. X is greater than 64, on a number line, I'm going to say, okay, 0, my domain said x needs to be greater than 0. My solution says that x needs to be greater than 64. So where on my number line does it work for both the domain and the solution? Wherever we see red and blue, it looks like it should be this right here. Anything greater than, I should label that, 64. So let's just test really quickly. So I could test it probably right now by, I'll use purple, by looping this. So 4 cubed, and I'll do this right here. Because I already got rid of the log there with my exponents. So x needs to be greater than 4 cubed. So if I plug in 63, 63 is obviously not greater than 4 cubed because this is a pretty straightforward problem. That does not work. But if I plug in 65, is 65 greater than 4 cubed? Greater than 64? Yes, it is. It seems like we got the correct region, x greater than 64. And that's me writing my final solution. So as we go through this chapter, we'll see a couple ways to test it directly, even without a log base 4 button on my calculator. Ways to test that log a little bit more directly than coming down here midway through my problem. But fortunately, we've learned how to get rid of that log base 4, so we can test that midway down the problem step. So find the domain. Whatever is inside your log, make it greater than 0. Solve the inequality. Like an equation, but make sure that you are keeping that inequality sign. On a number line, graph it, both of those parts, and test regions. Now this is important because sometimes with logs and exponents, the inequality sign will flip for a couple different reasons that I'm not going to go into right now. But testing those regions will help us catch any flips that we should have had, but we didn't. Finally, write your final solution. So what I have here is last problem, just for you to test your understanding of this concept. I'm going to pause and I want you to try to figure it out yourself. Actually, I'll give you two clues. There are two domains, one for each of those logs. So you'll need to find two domains and graph them both on the number line. And then it's a quadratic. And so you'll have to think about, we know how to solve a quadratic. Probably I would go factoring. Factoring's my favorite. There's also quadratic formula or completing the square, but you'll probably want to factor on this problem. I'm going to pause my screen, work this out. You pause yours, and then hit play, and we'll see if our work matches. All right, I'm going to resume my work right here because I realized there was one hint I didn't give you, and I figure I'll just talk about it right now. So on the right side of the screen in blue, I found domain 1. That was my domain for this log function. A squared minus 6 was inside the log function, so it had to be greater than 0. You can see my work there. I got down to a has to be greater than the square root of 6. Domain 2 was for this log function. A was the variable inside my log function, so it has to be greater than 0. Now in red on the left, I was solving this inequality, and I get to this point. I get to this point where we see that a squared minus a minus 6, which factors into a minus 3 times a plus 2, has to be greater than 0. So a couple ways to think about this. One of them is just to realize that 3 and negative 2 are the important points on my number line, put them there and then test a bunch. But I want to also talk about maybe a deeper level of understanding, something we can look for. If a minus 3 times a plus 2 has to be greater than 0, that means either both of those factors have to be positive, or both of those factors have to be negative, because a positive times a positive is greater than 0, a negative times a negative is greater than 0, but we can't have one of these negative and one of these positive. That won't work for us. So one way, and you don't have to think of it this way, you could just put 3 and negative 2 on your number line and test, but I would look at this and say, okay, so how would I make them both positive? I'm not too worried about this because plus 2, so anything like greater than negative 2, if I add 2 to it, it'll become positive, but minus 3. So what I'm thinking is to make them positive, a would have to be greater than 3. That would ensure that whatever is greater than 3 minus 3, that stays positive. And whatever it is, it's a positive number, plus 2 will be positive. So a greater than 3 takes care of the they're both positive idea. Or how do I make them both negative? Now it's flipped. I'm not worried too much about the minus 3 because that'll help me get it negative. But by looking at that second factor, I'm hoping you'll see a less than negative 2. Let's say it's negative 3. That would make this negative because it's more negative than the plus 2. And then obviously a negative number minus 3 would make it more negative. So this is another kind of deeper way of analyzing these problems, thinking both of those factors need to be positive or both of them need to be negative so that when they're multiplied together, they are greater than 0. On my number line, domain 1, a is greater than root 6. So what is the square root of 6? 2.4-ish, so between 2 and 3. So I'm going to say 0, 1, 2, 3. I'm going to call this root 6. So domain 1 said a is greater than root 6. Domain 2 said a is greater than 0. And my solution was that a is greater than 3 or a is less than negative 2. Now, looking at this graph, where does it work? It needs to work for both blues. But because red was an or, it only needs to work for one of them. So it looks like the region that works for all these criteria is right here, where a is greater than 3. That's my guess at a final answer. A has to be greater than 3. We can see, I'm going to change colors on my highlighter. None of this will work where I just X'd out to the left of 0 because it doesn't work well with this domain. Remember, the domain is the only place where this exists. we can't plug negative numbers directly into a log. We saw that earlier. So we know that none of that works. What about if I tried to plug like 2 in? 2 squared minus 6, it would break that. So I can't do anything less than 2. I could try 2.99, I guess, but then, again, going back to that higher level of thinking, if I plugged in 2.99, I would get a negative number for that first factor, a positive number. That'll give me a negative number, which is not greater than 0. So I feel pretty good about my answer of, what if I plugged in 4? Then looking right here, 4 squared minus 6 is 16 minus 6 is 10 is greater than 4. So yes, that works. I didn't plug any negatives into my logs. So again, we're looking at wherever on the number line fits the criteria that we found from our domains, domain maybe plural, and our solution. Write the final answer. A is greater than 3. So I realized that a lot was thrown at you in this problem, and that's why I wanted to pause and talk about kind of that hint. In class, obviously, we'll be talking about this as a group. But just looking at what we've gone over, all these ideas with logs, and maybe you've never heard the word logarithms before today, talking about how do we translate logarithmics and exponentials with the loop, how do we evaluate those expressions, how do we solve logarithmic equations using exponents because they undo each other? How do we solve them and check for extraneous solutions? Make sure that you don't plug in a negative into that function. And then finally, inequalities. We had 2 of those problems. So, crash course in logs, pretty much complete. Take a look at your practice problems. If you have questions, write them down, circle them so that you can ask when we are next together. We're going to go deeper in logs in 9.3 with properties of logarithms and ways we can manipulate them to make problems easier or sometimes just doable. But for now, that is all for 9.2. Bring your questions. Hope this made some sense. Take a look at those practice problems, and I will see you next time.